Hi, my name is Marc. I'm the Senior Director for Planning Control at Zoox. Today we take you through some of the busiest and complicated parts of Las Vegas.
Hi, my name is Ekaterina and I'm a Senior Software Engineer on the Computer Vision team. The drive that you will see today is fully autonomous with 0 disengagements. It was recorded on January 11th of this year.
All right, let's jump right in.
All right, and off we go. You can see the vehicle icon in the bottom panel. It just changed from gray to white. This is an indication that we just switched from manual to full autonomous mode.
I think there we will soon see a lane change, that we do it. And then you also see that we nudge around these intrusions. They're on the right side here again, like these cones that you see there. So we're not like totally tied to we always have to drive in the lane center. I think in the last video that you guys saw, we showed the capability of doing a right on red. Here we don't do the right on red because we have a red arrow, as you see. So this is why we stop and don't creep out actually. We are, of course, continually working on making our system better. Like every day it gets better and better. Yeah, and as you watch that video, you may notice, of course, small errors here and there. For example, slight hesitations in vehicle behavior. Yeah, and if the vehicle is in such a situation where the safest thing to do is slow down to determine the correct path, it will actually do that instead of just speeding through an uncertain scenario. We're moving again. There's some construction going on the right side, so again we need to nudge around it, make room for all these cones that are on the right side. We're passing other vehicles, so we actually have like a scene awareness where we know if we would, for example, go too fast past by somebody. So in here is an interesting scene. There was an undecisive vehicle on the right that we had to nudge around, so we had to go into the left lane a little bit to be able to clear that scene. So here we are about to go into one of the pickup and drop-off areas of an hotel. We let these pedestrians cross, then we go in. Yeah, pickup and drop-off areas are very unstructured, right? So a lot is happening, a lot of parked vehicles that you see over there. Pedestrians are getting inside and outside of their car. You just stop. Here we actually have some birds flying in front of us. So we like birds, right? That's why we stop for them and nudge around them. Now we go into that pickup drop-off area from that hotel. And as you can see here, we are like undecisive. Should we take the left lane, right lane? Should we do the lane change now? So the root cause for that, and that is something that we are actively working on at the moment, are actually these black cones that you're seeing. So what we have to decide is, do we go before that cone, after that cone? What is globally the optimum that we should have? Now we are here at the pickup drop-off zone. We see in front of us our lane is blocked. Pedestrians are still crossing. Now we are like, hey, let's get moving here. So we see there's a path that we could take to make further progress, and that is then doing the lane change. So we change the lane in order to make progress here, and that brings us then back on track.
Here the vehicle is aware of the stop sign and we stop before proceeding on our mission. This mission will take us from the hotel to the airport through the very busy multi-lane traffic that is common for Las Vegas.
All right, here we are approaching a left turn. And as you can see, even 2 lanes over, that is still a left turning lane, so Las Vegas is pretty big. And like you could ask now, hey, why don't we go into that empty lane? And the reason for that is, it's a cost tuning question, right? So there's a cost assigned to, hey, it would be good to get into that empty lane over there. But then there's also another cost that basically tells us, hey, later on in this route, you would need to do lane change again, right? And lane changes, as we know from our own driving, they are not the nicest thing to do. So that is why we say, okay, if you need to lane change a bit anyways again, and we have only, not a lot of vehicles in front of us, then it is a better decision to now stay behind that taxi that you currently see there to take that left turn. And there we make another lane change to the right. So in here it's pretty cool. As you can see, we take the lead vehicle in front of the lead vehicle. So just to clarify, when I say lead vehicle, I'm referring to the vehicle which is right in front of us in our lane. So that is the vehicle that you are following. Depending on how the occlusions are, even more than the lead vehicle. So that is due to our sensor setup, it's like mounted pretty high. So and actually also then an advantage that autonomous vehicle has to human driving. Here is a challenging junction. As you can see there, we need to yield to traffic coming from the left, so and they are pretty high speed. So this is where we need to have good perception to the left, left behind basically us, to be able to get into those streets.
Here is another example of what Marc mentioned, where we have a number of vehicles in front of us and we can actually detect them. At the bottom panel, you can see how many cars there are, both on the road and also in the parking lot, that our perception system is able to detect reliably. If you are watching closely, you notice the false positive pedestrian detection on our right. We bias our perception output to be conservative. That means that sometimes, if something resembles a human, like that palm tree, we may occasionally misclassify it as a false positive human. The 2 most important things here are that we detect every object around us, and that we also know which objects are on the road, the sidewalks, and in the parking areas, so we can safely proceed with our mission.
Oh, look, here's a nice example where we had to take a decision, do you want to stop or do you want to go through that yellow traffic light? And we reasoned about, okay, we still can comfortably come to a stop in front of that yellow traffic light, becoming a red traffic light, so this is why we came to a stop there. You saw the speed limit, it's 45 miles an hour. So we go all the way up to that road speed limit. The way our vehicle knows what is the road speed limit is currently based on our map system. So in our map, we know on which road we are on. And based on that, the vehicle knows, okay, that road is a 45 miles an hour road, and that is then the maximum speed that we would go then on that road.
As we drive with high speeds in Las Vegas, it is important to be able to detect other vehicles far away. Our perception stack has this capability because we use 3 different kinds of sensors, and therefore we can detect vehicles so that we can react safely in time. Here we took the off-ramp on our left to navigate down to the main area of the airport.
here we are coming closer to the airport, and that is something nice about Las Vegas. You have the strip right next to the airport. That is something nice about it. So, you have a fairly small geofence, but a lot of interaction is going on exactly in that geofence. Here it's actually interesting. There's a parking house structure, which obviously, like localization challenges are in such structures. So you can see that we master them pretty well.
You might wonder how a Zoox vehicle knows where to drive. When a Zoox vehicle comes out into the world, the first thing we do is unstructured calibration. What this means is that we know where the cameras, the lidars, and the radars are positioned on the vehicle so that we can correspond a car in a camera to the same car in the lidar and radar data. The next step is to map the area that we will drive. This map includes information like the roads, the traffic lights, the stop signs, the speed limits. Once we have this map, we can now localize, that is, we know where we are located at each point in time by using our sensor information along with the map that we have computed.
Yeah, so we are still within the airport, now coming up to where we would pick up passengers. And of course, they're same as for the hotel pickups and drop-offs. It's always very busy, very unstructured. People, like unpacking and very hectic. These are like big challenges in Las Vegas, especially.
While we don't show fine-grained classification, in these cases we do also recognize when people have luggage with them as well, so that we can safely maneuver around them. And here we see a number of cars where people are coming out of the cars with open doors. And we do recognize open doors again so that we can maneuver safely around them. As you saw a few frames ago, when pedestrians were crossing, carrying their luggage behind them, our system groups the luggage with the pedestrian because this is part of the same system, and this way we can make sure that we are safe around both the pedestrian and their luggage. As Marc pointed out, it is actually very important to be able to detect when a car door opens and a pedestrian comes out of the car. We see these situations very often, and we detect them using our perception stack, and then Planner can safely navigate around such situations.
So Kate, you just mentioned Planner, and I thought I'd explain what it means really quick, like plane control, what does it mean at Zoox? So on the highest level, at first we need to define how do we get from A to B, which set of roads do we want to use. Then the vehicle starts moving and needs to reason about the environment and needs to reason about also other traffic participants. So we need to take decisions like, do we want to follow that vehicle, do we want to nudge around? And then we generate a trajectory, feed that through the trajectory generation and also through the lower level controls to then output how much steering, how much motor torque and how much brake torque do we want to have.
Another difference between San Francisco and Las Vegas is the speed limit. Because San Francisco is so dense, we have much lower speed limits. But in Las Vegas, we drive at like 45 miles an hour. This requires that we are able to correctly detect and predict where vehicles will drive so that we can react safely at these higher speeds.
Yeah, so lane changes are another very tricky and interactive, collaborative maneuver that our vehicle executes. So when you lane change, you need to, of course, take into account, like, if I do that maneuver, what or how does the other traffic participant that would, either block or come in from behind, how would that person need to react in his or her vehicle? So, and this is also a nice thing of our stack. We actually calculate that and also weigh that in costs. How drastic would that person need to react to us? In our latest software version, we can actually do that even more elegant. Like you saw here, we would do like 1 and then 2, but now we can do that more elegant and do that in a smoother way that it is not as discretized as you saw it there. So at the next traffic light we need to take a left turn, but we actually want to be in the very right lane out of the left turning lanes, because later on we want to be in the right hand left turning lane. This is why we stay here in this lane, even though like the lanes to the left or to the right they go faster. But for our mission, quote unquote, it is best to stay in this lane here.
In Las Vegas, we have many cases where intersections will have a number of turning lanes like this one. It is common that cars decide to change lanes while making a turn, sometimes even cutting us off. This is a challenging situation because we have to predict when this might happen, and we need to know what is the best evasive action to make so that we can remain safe. So it is important to be able to correctly recognize construction zones because they can happen anywhere. However, here you see that we have cones that are on the side. They don't actually indicate a construction zone. So simply identifying that these things are cones is not sufficient. What we do is we also understand whether this is an actual construction zone or if these cones are just put on the side, so we don't stop for them.
Yeah, there are a lot of cones. Las Vegas actually, when you drive there, they have a lot of construction, or like day or night construction, I don't know how they call it, going on. So in the night you come there and boom, like a whole block out of these, 4 or 5 lane roads. Sometimes it's completely blocked off and you need to be able to route accordingly. And there, Ekaterina, there's an interesting traffic light there in the front. You see that? Like these are like, I think it has 5 possible lights or something.
So different locations, different states, they could have different kinds of traffic lights because the road structures are very different, like you point out here. And we are able to correctly detect and classify these traffic lights. And also because we are using a map, we know exactly which traffic light is for which lane so that we can follow the correct traffic light. So here you would see that we have pedestrians on the sidewalk right next to the crosswalk. It is very important that we not only detect pedestrians correctly, but that we also correctly predict when and if they will cross in front of us. This way we can either drive without stopping if they continue walking on the sidewalk, or we can stop and yield to them if they're about to cross.
All right, and we approach another pick-up and drop-off for the hotels, getting in line to get through it. And the hotels in Vegas, they vary a lot. Like this one here is a little bit more structured, so they have like these lanes. Sometimes it is just a big pile of whoever goes first goes first. You see here, there's a pedestrian already crossing, other pedestrians are coming, but we decide it is safe and fine that we go. We're not on the total conservative side, so that we would not make enough progress. And here, that is also a nice scene. So you see that a lot of vehicles wait for the traffic light, but we can actually go. What humans also do is they don't blow past all this slower traffic. So we have actually a machine-learned model inside of our planning stack that takes in the scene around our vehicle, and based on that, it is able to determine a maximum speed and a maximum acceleration limitation so that we don't blow by all these vehicles.
Here you see on the side that there are many pedestrians. Our system is able to correctly identify each pedestrian and track them across sensors. In Las Vegas, we often encounter double-decker buses like this one. They present a challenge because they can occlude traffic around us, making it more difficult for us to predict what is going to happen. Sometimes they also occlude traffic lights. The 3D map that we use to drive does not know about occluding objects. However, our sensor setup has a 360 degrees field of view of the world, and we can see some of the traffic lights. In addition, our perception system knows when objects are occluded by other objects and can reason correctly about the world. Marc, how does Planner deal with situations when there are occluded objects?
Yeah, we basically consume we call it occlusion grid from our perception friends. So we can reason them about those occlusions, because then we know what we don't know, right? Like the unknown is now a known. And there you can see, for example, at junctions that are occluded, either by buildings or by parked vehicles, we adjust then our plan in the way that we are a lot more cautious in how we move, so that we can get to know more, right? Like we creep out to make sure we can see that area that is occluded. And once we know that we can see far enough so that it's safe to proceed, then we actually proceed. Same for occlusions when we do like right on red turns, for example, where we also need to make sure that we know we can see what we need to see so that we can proceed.
Here we can see large groups of pedestrians both on our right and also across the road, and our perception system can correctly identify all of them. Furthermore, this is a very crowded scene with a lot of vehicles and pedestrians, and we still operate in real time. It is important to be able to recognize traffic lights from far away in Las Vegas, because we're driving at much higher speeds compared to, say, San Francisco. In the previous intersection, it was actually very hard for a human to tell what the traffic light state is. However, our perception system does so perfectly.
Yeah, here you can actually also see the lanes here are a lot more narrow than just a few minutes ago. We have to adjust our driving speeds for that, of course, so to account for tighter lanes.
So, as you're driving through Las Vegas, it is easy for you to get distracted. Here is a wonderful example where this car decided to change lanes right in front of us. Our autonomous system does not get distracted by the tourist attraction around us, and it is able to perceive the world and predict the agent's actions around us. It looked like the vehicle that cut in front of us was going super fast, but recall that this clip is sped up by a factor of 2. Notice the construction cones on our left. Even though we have a detailed map of the world that indicates this is a driving lane, our perception system detects the construction blockage, and we understand that we cannot drive in that lane at this time. Yes, and construction zones are challenging because they're dynamic things that happen in the world. So using our perception system, we can correctly detect when there's a construction zone, which lanes are blocked off, so that we can plan around them and continue with our mission.
Yeah, one really cool thing about our purpose-built vehicle is that it is a 4-wheel steered vehicle. So that means both axles, the front and the rear axle, can be steered. And what that buys us for us, I mean, next to adding stability to the vehicle itself, also in pickup and drop-off maneuvers where we need to fit into tight spaces, like the parallel park kind of thing. That is where we can make use of our 4-wheel steering to really fit into tight spaces, to have a good experience for the customers, and that we can drop them off. So our vehicle is like highly maneuverable, which is a pretty nice advantage to have.
While some scenarios still pose a challenge, our stack is improving every day. Here we're about to make a U-turn. Marc, can you explain why this is a challenging thing to do?
We stopped there because we were confused about a vehicle which was already on the other lane that we are U-turning into, and did not know yet what to do with that vehicle. Yeah, U-turns are tricky because if you look at it from a coordinate system, you basically return in one coordinate back to where you already were. So you make the U-turn, and that leads to tricky situations that we are currently actively working on to master the U-turns. And you can also see it's like it requires a very high steering angle and angle rate to get around there. So it's a very tight U-turn that we have to do there.
Once the traffic light turns green, we execute the U-turn perfectly. Here you see another example of where the truck that is in front of us was occluding traffic lights here as well. However, because our sensors can still see some traffic lights, we're still able to reason about the state of the intersection and follow the traffic rules.
What is so nice about Las Vegas and why it's so interesting for us is that on the one hand, it has, if you look at the size of the geofence to have a viable product, it's actually not too big, right? It's actually fairly small if you compare that to other cities. You have the airport right next to the strip, and most of the customers would go then from the airport to hotels, from one hotel to the other hotel, or to a show which is also directly at the strip. Another nice thing about Las Vegas as well, there are a lot of cases you have the pedestrians quite separated from the actual traffic, which also makes it nice. Obviously, it's also different to San Francisco. San Francisco, everything is very narrow. Usually you don't see so many lanes going into the same direction. You would see either one lane, maybe two, but that's it. Las Vegas is, in comparison to San Francisco, also very flat. So San Francisco, everything is uphill and downhill. Here you have it fairly flat, which is also very nice. So the traffic in Las Vegas is more structured than the traffic in San Francisco.
So here you see yet another example of just how busy Las Vegas is and how capable our system is tracking seemingly countless vehicles and pedestrians all around us. Once again, we're surrounded by traffic. Here we are in 6-lane traffic traveling in our direction. We're also tracking traffic over to our far left, traveling in the opposite direction, while simultaneously tracking all of the pedestrians around us as well. Las Vegas is a fantastic place to test and validate our system. It is different from San Francisco. For example, we have very different kinds of traffic and also traffic rules because the locations are in 2 different states. We also have different climates, and the pedestrians that we see on the streets actually are in very different kinds of groups in Las Vegas compared to San Francisco. Furthermore, in Las Vegas, we have many very large lanes that require that we can do lane changes in a safe manner.
Yeah, one really cool feature about our planning and control stack is that it is, we call it like a hybrid stack. That means for us, we have machine learned features in there and also more heuristics-based, so classical programmed features in there. One of the examples that is in our drive that we show you is the scene awareness, right? Where we actually, based on the scene around us, we learn a speed that the vehicle should drive and acceleration that we should follow. Yeah, and the nice thing about that is that we have an easy time to exchange heuristics-based feature with machine learned features and also be able to compare them. Here you might ask yourself, how do we actually know how to keep the distance or how to follow a vehicle at a safe distance? So at first we calculate what is the desired distance that we would like to follow in. And that is based on a time gap and our driven velocity. So then we compare that to the perception output, like how far is that vehicle away and what's the relative velocity, what is the acceleration of that vehicle, and also take predictions into account. And based on that, we calculate then what is our desired velocity that we would like to drive and what's the desired acceleration.
Here we can see a large number of pedestrians again, and we are able to really distinguish between them on both our left and our right. I remember 3 years ago when we first started driving in San Francisco, we actually had a lot of difficulty identifying individual pedestrians, but we're doing much better now.
I just saw like the traffic light on the right there it was flickering from red to green to the green arrow. Ekaterina, can you explain us what's going on there?
Yes, so those two traffic lights are actually for the traffic on our right. You see the cars that are turning. So they're rotated a little bit to the side, so it makes it more difficult for us to recognize what the state is. However, the traffic lights for our lane are in front of us. They happen to be occluded by these big buses. However, we're still able to reason about our traffic light intersection correctly. Here we are making our way through fast-moving traffic on 1, 2, 3, 4 lanes, and in a bit the road will expand to 6 lanes. Here you see that the black truck in front of us cut into our lane, so we safely slowed down to make room for him to change lanes. We are now leaving the dense traffic and winding back into the hotel drop-off zone as we near the end of this drive. And now we're coming back to where we started. Notice that the vehicle navigates this narrow passage between another car and a cluster of pedestrians, then waits for the car in front to leave, pulls over into the parking lane, successfully completing the mission. Once the vehicle is stopped, the autonomous system disengages and you'll see the icon turn from white to gray, indicating that vehicle control is now back with the safety operators.